Actually, right here. All right. So today we're going to look at a couple things. The first thing we'll do there we go. Okay. So we'll just call this evaluating limits. It's kind of like a continuation of what we did on Friday. Again, we have three methods that we talk about, right, to evaluate limits, like three kind of categories, I guess I'll say. We have the numeric method, bless you. That's what we did with the tables, right? We'll have the graphical method. We'll see that a little bit later about how we're going to do that. And then we also have the analytical method, which is like direct substitution, and then this technique I'm going to show you too. This one would kind of fall under the analytic method, where you basically are just kind of like doing the math to cancel and simplify and make it so that you can evaluate the limit using direct substitution, essentially. Okay, and so one technique here is called rationalization. Okay, rationalization. And you'll see what I mean here. So let's say we want to evaluate the limit. We'll just jump in with an example to kind of kick us off here, to kind of pose the problem that we're going to have. So evaluate the limit. And we'll say our limit here is the limit as x approaches 0 of the square root of the quantity x plus 1 minus 1 all over x. Alright? So, first of all, right, when we come across a limit in the wild and we want to try and evaluate it, we should maybe try direct substitution and see if direct substitution works. Does direct substitution work here? No. What do we get? 0 over 0, right? If I plug in a 0 here, it's going to be 0 plus 1, right? If I plug in that 0, direct substitute, 0 plus 1 is 1. The square root of that quantity 1, well, square root of 1 is 1. It'll be 1 then minus 1, so we have 0 in the numerator and then 0 in the denominator. So 0 over 0, indeterminate form. Direct substitution doesn't work. All right? Besides that, we could also go to our graphing calculators, right? We could like type this thing in and use our table. That's another option that we have. I guess I should close that. All right, so I'll just show that to you here real quick, or slow, depending on how I can type things. So let's see here, the square root of x plus 1 minus 1. Of course, we want that whole quantity in parentheses all over x. I go to my table, and then I'll approach 0. So approaching 0 from the left would be like negative 0.1, and then negative 0.01, and then negative 0.001. Okay, of course, I type in 0, I get an error. And then I'll approach from the other side here too, so 0.001, 0.01, and then 0.1. Okay. And sure enough, from our analysis here, it looks like we are actually approaching a number here. What value does it look like that function approaches as x approaches 0? Yeah, 1/2 or 0.5. So like maybe this is equal to 1/2 here. Maybe this is like 1/2. Maybe, right? Maybe it's equal to 1/2. Okay. We could try and get in closer and closer and closer and just see, but in fact it looks like it was 1/2 here, right? We're pretty well convinced right now. So there actually is a way to simplify this thing in such a way that we can then use direct substitution. Okay, and you get a hint there with the idea of rationalization. So the way we can do this by hand, because of course this could show up on a non-calculator kind of question, and then we wouldn't really be able to use a table easily. Okay, so I'll rewrite the problem here. And so what we're going to do here is multiply this thing by the conjugate, all right? And the conjugate is just, right, a fancy word there for, we're going to take this numerator quantity here and multiply it by x plus 1 plus, or the square root of x plus 1 plus 1, like that. Okay? And then because, again, we don't want to change the value of this limit, we can't just like bring in this quantity, the square root of x plus 1 plus 1, and multiply it over. We need to we don't want to change the value, so we'll really just multiply by the value of 1 here, right? Or just this thing simplifies to just 1. So we're going to take this and multiply it by 1. Okay. Have you guys done something like this in previous classes before? Is this like familiar at all from like Algebra 2 maybe or anything? Kind of ish? Yes? Okay? No? I don't know? All right. Silence? Gotcha. So the reason why we do this, right, just to refresh your memory a little bit here, why this works is that, well, if you look here, we create what kind of scenario have we created here? A difference of squares. Exactly right. You can see that we have a quantity, we call this thing A, and the very same A over here, we have a B, 1, and the same B over here, 1, but it's A minus B here, and it's A plus B here. So we know we multiply these two things together, we're going to end up with A squared minus B squared. And that's important because we'll be squaring this square root and allowing it to be kind of canceled out there. Okay? I'm going to write this first one out very explicitly so you can see like all the inner workings of it, and then from here out, from beyond this one, I'll just do it, the shorthand way kind of thing. So what I mean by that is, so I'm going to actually FOIL this thing out. So we have these two terms. We'll do the first, right? Square root of x plus 1 times the square root of x plus 1. So that's going to be the square root of x plus 1 squared. And then the outer terms, 1 times the square root of x plus 1. Then the inner terms, minus 1 times the square root of x plus 1. And then the last terms, negative 1 plus 1, so it's minus 1. All over. Now, my recommendation here is that you don't distribute the x, right? The x is going to multiply to both of these terms here. But what I would recommend is you just leave it undistributed. And just put that square root of x plus 1 in parentheses like that. And you'll see why I recommend that you leave it undistributed there. You don't distribute that x to both terms. Okay? And again, if this is more comfortable for you, right? If when we do some later ones, and you're like uncomfortable with like going straight from here to then what this thing simplifies to be, that's fine. You write it out. You take the extra steps if you need to. But the beauty of this is that those middle terms cancel, right? And when we square that square, because it's a positive 1 root x plus 1 and negative 1 root x plus 1, and when we square that square root, it cancels. And so we're left with just x plus 1 here, right? Squaring that square root with just x plus 1, and we're left with a minus 1. That's all that's left in the numerator there. Over, and then we have x times the square root of x plus 1 plus 1, like that. Okay. And so then we can do 1 minus 1. They cancel too. Okay. And so we have x over x times the square root of x plus 1 plus 1. And now what can we do? The x's cancel, right? So you can see why I didn't distribute the x, why I asked you guys or suggested we don't distribute that x first, because they're going to end up canceling out, and we might not have seen that had we distributed there. So that's why I did that. So we end up with 1 in the numerator, right? When you simplify, it's simplified, right? When you can't cancel out, it's division here. So x divided by x is just a 1 over then the square root of x plus 1 and then plus 1. Can we direct substitute now? Yeah, we can, and it works. Or more importantly, it works, right? I guess you can direct substitute any point, but it works here. We plug in that 0. And again, please, take your time with these. I know it's like frustrating to have to fill up half your paper with a problem maybe or something like that, but I mean, if you get it right, that's important. Get more comfortable with these before you start trying to skip steps. All right, I mean, maybe if you need to, just like do it. Okay, it'll be then 1 over the square root of 1 plus 1, which is then just 1 over 1 plus 1, which is then 1 over 2. And we finally get down to the answer that we expect, 1/2. Okay, and now we can for certain say that yes, the limit is 1/2. The limit as x approaches 0 of that function was 1/2. Okay? Questions on any of that? Alright, we'll do one more, and then I'll have you guys try one. Alright, we'll just do one more of these, and then I'll have you guys try. Okay, it's pretty satisfying, right? Get all that work on your paper. Why are you laughing? Alright, anyway, moving on. I guess that's why I'm a math teacher. Alright, the limit as x approaches 2 of x minus 2 over 3 minus the square root of x plus 7. Alright, so does direct substitution work? Yeah, well, let's see. If I plug 2 in the numerator, I get 0, which is not a problem. 0 in the numerator, no problem. But if I plug 2 in the denominator, I get 2 plus 7, 9, square root of 9, 3, 3 minus 3, 0. So I end up getting actually 0 over 0. So that's a problem. Right? 0 in the numerator, no problem. If I get like a 0 in the numerator and some other number in the denominator, that just means my limit is approaching 0. That's fine. But if I get 0 over 0, that's a problem. That's the indeterminate form. So, alright, well, again, how do we know we're supposed to use this rationalization technique? Well, the hint is that if you see square roots and direct substitution doesn't work, then that's the next technique you want to go to. Doesn't mean it's always going to work. Sometimes it won't. But that's the next technique you go to again, these are just like tools in the toolbox. We, pull them out and see if they work. Try it on our problem here. Okay. Kind of like what we did with polynomials when we were trying to find zeros and all those different techniques that we had, or quadratic. So I'll multiply by 3 plus the square root of x plus 7 over 3 plus the square root of x. And it's just the opposite. Instead of 3 minus the square root, it's 3 plus the square root to create that difference of squares scenario. Okay. So now if you'll permit me, I'm going to skip a couple steps here. I'm going to just jump right into the product of this thing. So I know, again, because it's a minus b and this is a plus b, I'm going to end up with a squared minus b squared here. So I know that I'm going to end up with a 9 minus, and then the square of this square root will just be the quantity x plus 7. Okay. And then in the numerator I'll have an x plus 2 times the quantity 3 plus the square root of x plus 7. Okay, again, I'm not... Oh, why did I put that x plus 2? It's x minus 2. There we go. Okay. Very important here. Okay. We're subtracting the quantity x plus 7. Right? The a minus the b times a plus b there gives us a squared minus b squared. So that's going to be 9 minus, and then the quantity x plus 7 squared, x plus 7 squared. So it's minus the quantity x plus 7. That minus sign distributes. The minus distributes. Alright, so let's simplify here. Alright, we get the limit as x approaches 2 of x minus 2 times 3 plus the square root of x plus 7. Okay, so if I distribute the minus sign here, I'm going to have, and again, I'll take the time to take the steps here. We have 9 minus x minus 7, which if I write another step here, we get x minus 2 times 3 plus the square root of x plus 7 all over. Now if I combine my like terms in the denominator there, what do I end up with? Combine my like terms in the denominator here. What do I end up with here? Is it going to be x minus 2? There's a negative sign in front of that x. So it's a negative x, and then 9 take away 7 is negative x plus 2. Uh-oh. That is not the same thing as x minus 2. They are not equal. So they don't cancel. So what do? Give up? Oh my gosh, what? Factor a negative out of the denominator. That's right. You thought you could just stop, but you were wrong. Yes, we can factor a negative 1 out of the denominator, right? This thing, this negative x plus 2, is exactly the opposite of positive x minus 2. If you factor a negative 1 out, okay, we're left with positive x minus 2. And wow, now they can cancel. Okay, so we have the limit as x approaches 2 of 3 plus the square root of x plus 7 all over negative 1. And now we can finally try that direct substitution we've been waiting to do. And we get 3 plus the square root of 2 plus 7 over negative 1, which is 3 plus 3, which is negative 6. So yes, the algebra went from like a 2 to like an 8 or 9 or a 10. I know. All right, we kind of went from like 0 to 60 with this algebra and stuff. But there it is. All right. So let me give you guys one to try. All right. Any questions before I give you one to try? Any questions before I? So, well, you can always just ask me too because I walk around. All right. Anyway. All right. Special delivery from Mr. Widmeyer to you. Limit as x approaches 0 of the square root of x plus 9 minus 3 all over x. Okay, so go ahead and give that one a try. And I'll do 2 here real quick, so I can come around and help. Bless you. So technically here we want to make sure we subtract the 9 first and cancel the x. Because it has x plus 9 there, and minus 9, you want to cancel this, yeah. So we use 9 minus 9, so we use x over x instead. When the x cancel, what's cancel these? Mr. Widmeyer,
You're multiplied by x plus 9 plus 3. X plus 9 plus 3.
Like what was it?
So
We did the conjugate.
I did the conjugate. We got down to like this point where we combine our like terms.
Was it originally x minus 2 over 3 plus?
Yeah, let me show you here because that way. Well, I'll bring it over because I don't. This was your original. Okay. So, we multiply the conjugate of this thing.
I don't.
Oh yeah, I think I like
equals
remember seeing that, and for some reason I thought that we had to like
and
multiply
then
the
I
x
would
minus 2
do.
on the top line, but we didn't.
Oh.
Right, no.
Like
Yeah,
once
so
you get
it's
the
just
final
like
answer,
that.
the limit.
Oh, that answer, that
But I
is-
just keep putting equals, times what it does.
Okay.
Where are you?
Alright, so this.
What did you multiply that? Alright, so I started doing bottom.
That's the square root of x
You
plus
could,
9, right?
or you could just like
And that's the square root of
multiply
x
it out.
Yeah. So
I
that's
think
like.
FOIL
That's
is
x plus 9.
you're doing x plus 9 times square root of x plus 9 times the square root of x plus 9. Yeah. And then just say, it's the square root of x plus 9 squared.
Negative 3 times
And then I have a
positive
minus 3 plus 3 is just negative 9. Yeah. And then the plus 3 x plus 9 minus 3 x plus 9, those cancel out to 0. Does that make sense? At the bottom. No, on the top.
So, right,
X
because
plus
again,
9
no matter how you're
minus 9,
multiplying,
right?
This
Because
times
the
this.
other two cancel.
The square root of x plus 9
So then
will still be there,
yeah.
so you would have x square root of x plus 9.
And then the bottom,
So you would have the
kind of keep it.
But then this one, it just appears in numerator, because the root x plus 9 times the root x plus 9. That's the root x plus 9 squared. Okay, now, these don't cancel like that, but you do want to simplify the numerator.
You got rid
So far, so
of
good.
the
Denominator, that's right.
keep it
It'll be,
parentheses.
so root x plus 9 times root x plus 9 will be root x plus
0
9
plus
quantity
9
squared.
with the square root of
Right?
9.
So that's
squared,
going to
the
be
square root of
just
that
x
is
plus
3.
9.
Now I got x over x.
Right, let me do it up here. I'll show
3
you.
square root of 3. Yeah, you just got it. What? Put it in parentheses. The x plus 9 squared. Not, like, don't have that extra factor down.
Right, you're more worried about how to multiply the numerator. That's what it
Then
is.
this.
And again, my recommendation, if you're not able, if you're having trouble jumping from this then just to what it's going to equal, just boil it out. This is, like you have your first term here, so the first term will multiply. So it's going to be squared, so you multiply by 1. The outers will be plus 3 root x plus 9. The inner, minus 3 root x plus 9. The last becomes plus 3. Okay, I'll multiply it all out, because now you can see very much more clearly. Those cancel, and that'll be just and then minus 9. This plus x. Does that make more sense? All right. Let's proceed forward here. All right. But we should end up with 1/6. Okay, 1/6 there, 1/6. All right. Any questions on that one? All good? All good? All right. So if you want to flip your paper over then, we'll take a look at evaluating limits graphically. Okay, so here's a graph. Okay. There's no one function that defines this thing. This is more than likely a piecewise function, all right? But I'm just not giving you the piecewise function here. Just the graph is what we're looking at. So we'll just kind of do some of these. Okay? Let's take a look at some of these here. So, number 1, all right, let's just try evaluating the limit. Again, we'll call this function f of x, right? So this whole thing, taken in its entirety, will be called f of x, the function f of x. Okay. Most likely a piecewise function. And let's just say the limit as x approaches negative 2 of f of x. Okay. So, as x approaches negative 2, let's look at our graph here, right? Our graph, as we get closer to negative 2, we're going to be utilizing this kind of like linear piece of the graph, right? And as we get close to that negative 2, we're going up and 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 up, right? Likewise, as we approach negative 2 from the right, it looks like it's kind of like a quadratic piece, and we'll approach it from the right, so coming up, 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 up. What is the y value that we approach as x approaches negative 2? 3. The limit here is 3. Okay? The limit here is 3. Compare that what is the value of the function at negative 2? Not what is the limit as x approaches negative 2. What is the value of the function when f is precisely negative 2? 4. You have a point here, right? So at precisely negative 2, up through the hole, right? Because it's a hole there. We go up to the point that's actually existing at y value 4. Okay. So in this situation, right, we go back to that idea of direct substitution, right? That direct substitution is a technique we use to evaluate limits. Direct substitution is very similar to evaluating the value of the function, right? Very similar. Except in situations where our function is discontinuous. Our function is discontinuous at negative 2, right? We have a hole and then there's a point up there. It kind of like jumps up a little bit just for an instant. And so that's why it makes sense here that the value of the function is not the same as the limit. Okay? This is why we can't use direct substitution in situations where the function is discontinuous. At those discontinuities, other behaviors can occur, so we can't say that the value of the function is the same as the value of the limit at those negative 2. Okay? Let's try another one here. And I'll kind of like pair these up. What about the limit as x approaches 1 of f of x? What will we say that equals? James say 0. Okay. So again, let's check that. Here's the quadratic piece. Okay, and there's x value 1. Let's check. So we approach that 1 from the left, and it's kind of coming up towards the x-axis there. And we approach 1 from the right. Maybe it's like a piece of a cubic, or actually no, like the rational function of 1 over x or something like that. And again, we come up from the right. It's going in towards that, and yes, the y value there would be approaching 0. And then, just as I did before, let's evaluate the actual value of the function. What is f precisely at 1? Not when x is approaching 1, but when x is exactly 1. What is the value of the function? 0. Yeah. This should also not surprise us. The function is continuous at 3. Yes, it's a bit pointy, but that's okay. Okay? The fact is, right, continuous, again, in your informal understanding of continuity, I can take my pen and trace over without having to pick it up at any point. Here, to draw this, I had to like trace my pen, pick up my pen, put it back down, pick up my pen, put it back down to continue. But here I can just continue, one smooth curve. And so the direct substitution idea works, right? Evaluating the limit at 1 is just like evaluating the function at 1, same value. All right, let's try one more here. Excuse me, what is the limit as x approaches 3 of f of x? One thing here. Okay, right, it goes to negative infinity from the left. What about from the right? It goes to positive infinity. So left-hand limit, right-hand limit, disagree, and so what do we say about the limit? Does not exist. The limit does not exist. Okay? And in fact, even if both of them went to positive infinity, or both of them went to negative infinity, to say that the limit of something is infinity is kind of like, I don't know if I want to say paradoxical, but to say that something's limit is infinity means that it has no limit in the first place. And so you can't say something's limit is infinity. I mean, you can like evaluate still, because it is, sometimes helpful to evaluate whether it's going to positive infinity or negative infinity. But to say something's limit is infinite, implying there is no finite limit, right? It just continues on. That would really say the limit does not exist, okay? And so also, let's do the same thing we did before. What is the value of f precisely at 3? What's the value of the function? Does not exist. Does not exist. Okay, so key summary here: the existence or non-existence of f of x at x equals c. Okay, so that is the function value, the existence of the function value or the non-existence of the function value at a particular x value, c we'll say, has no bearing. Okay, has no bearing on the existence or non-existence of the limit as x approaches c of f of x. Okay, that's kind of an important summary of this exercise, something I try to emphasize, right? In our first two problems, they both existed, but they were different values, right? Limit in the first, in number 1, approached 3, whereas number 2, the value of the function was actually 4. At the same, approaching x equals -2 or equaling exactly -2, right? Two different values. In the case of 3 and 4, right, they were the same, so it happened to be that way. And then 5 and 6, they both didn't exist, but for kind of reasons. So just something to keep in mind there. Okay, evaluating a function is very similar to evaluating a limit with direct substitution, but it's not always the same. All right, one last thing. One last thing here. Yeah, I just want to squeeze this in. All right. And we'll hit more of this here too, but limits at infinity. Okay. Actually, yeah, I do like this. Okay. Limits at infinity. Okay. So what I mean by that is the limit as x approaches positive infinity of f of x. Okay, or the limit as x approaches negative infinity of f of x. So believe it or not, right, even though x is going off to infinity, right, so x is infinite, the value of the function sometimes can approach a finite number, right? We saw in our end behavior, which is essentially like a limit idea, as x approaches infinity, we always were getting values of either f of x approaching positive infinity or f of x approaching negative infinity. But I told you that there were certain situations, certain scenarios where when your x value approaches infinity, you will approach a finite number. It approaches just a single number, right? And so we'll look at that here right now. Or the same, likewise, with x approaching negative infinity. And so here are the guidelines, and you may remember this from Algebra 2. So believe it or not, you were kind of evaluating limits in Algebra 2, and you just didn't know it. Okay, so the guidelines for evaluating limits at infinity. And this is for rational functions. Okay, we've already seen with polynomials that really you just use that, the lead coefficient and the degree to help you evaluate the limits. The idea there. Okay. Number 1, if the degree of the numerator is greater than the degree of the denominator. Okay? If the degree of the numerator is greater than the degree of the denominator, the limit as x approaches infinity or limit as x approaches negative infinity does not exist. Okay? If the degree of the numerator is greater than the degree of the denominator, the limit does not exist. Okay? That would cover all of our polynomials, right? That covers all of our polynomials, because every polynomial you can rewrite as a rational function, just put it over 1, right? And so the polynomial will be up in the numerator, and its degree would always be greater than the degree that just the number 1 is the degree of 0. So it's always that greater than that degree. So that's why our end behavior for polynomials always goes off to infinity or negative infinity. Therefore, their limits don't exist. Okay. If the degree of the numerator, I'm going to abbreviate this point. Okay, the numerator of these. So degree of num is equal to the degree of denom. Okay, so the numerator and denominator degree are the same. Do you guys, anyone remember what will this equal to? It's the ratio of the lead coefficients. Okay. This is essentially the horizontal asymptote stuff. You guys remember doing horizontal asymptotes last year? Or in Algebra 2, I should say, maybe it's not last year. Algebra 2, talk about horizontal asymptotes. You guys did talk about horizontal asymptotes, yes? Yes. Okay. So anyway, this is the same idea here. And then the third scenario, well, we talked about when the numerator is greater. We talked about the numerator is equal. So then when the numerator is less than the degree of the denominator. Okay, and that is again, the limit as x approaches, and I'm going to put plus or minus infinity because it'll be the same thing either way. It's going to approach 0. Okay. And so we'll look at a couple examples here. I'm sorry for going so late. Sorry for going so late here. Okay, so the limit as x approaches infinity of 2x plus 5 all over 3x squared plus 1. Okay. So again, we can see here this is the limit at infinity, right? We are approaching infinity, x approaching infinity, so we want to go to our kind of rules here, our ideas, okay? So let's see. In this case, the degree of the numerator is 1, the degree of the denominator is 2, right? The highest powered term here is a power of 1, the highest powered term here is a power of 2, and so the degree of the denominator is greater, right? The degree of the numerator is smaller than the degree of the denominator, and so we would say that this thing approaches 0. Okay? Degree of numerator is less than degree denominator. Okay? That's the first one. We'll do 2 more here real quick. The limit as x approaches infinity of 2x squared plus 5 over 3x squared plus 1. For number 2, what is the degree of the numerator here? 2. What's the degree of the denominator? So they're the same, which means our limit is going to equal what? 2 over 3. The ratio of the lead coefficients, 2/3 there. Okay? Last one. The limit as x approaches infinity of 2x cubed plus 5 over, that is supposed to be a cube here, I'll make it bigger, 2x squared plus 1. Okay? What's the degree of the top? 3. Degree of the bottom? 2. So in this case, the limit does not exist because the numerator has a greater degree than the denominator. Okay? All right, for homework. For homework. it's going to be page 859, numbers 29 to 34 and 76. Page 868, numbers 5, 7, 21 to 27, the odds. Bless you. And then page 887, 9 to 27 odds. Okay? And of course, that'll be on the Google Classroom today, as well as it's in the calendar too. Okay. Again, I apologize for not getting you guys time to work on this in class.